sometimes the last day is the greatest day. This morning we have very excellent speaks about bootstrapping related to homomorphic encryption. So the first paper is about improved third circuit synthesis with multi-value bootstrapping for FHEW-like scheme. The speaker is Ioannis Mono. Let's welcome our speaker.
All right, good morning, everyone. Pleasure to be here. Nice to see a couple of faces, even after the morning after the rump session. Always nice. Thank you for the introduction as well. We're going to talk about improved circuit synthesis with multi-value bootstrapping for FHEW-like schemes. This is a joint work with Kamil Kluczniak, who is now at SecuNet Security Networks, and with my supervisor, Tim Gunesu. Yeah, we are in the context of privacy-preserving computation. We have encryption at rest, which we kind of solved already. We have AES, and like everything is pretty nice there. Sometimes stuff breaks in practice, which we like to do here at CHES as well. But yeah, we're doing overall fine. We have the same thing for cryptography or data in transit, where we have mostly figured out how to do this and now are future-proofing it for post-quantum security. And then we have a big new exciting topic of how do we actually protect data that is in use. And one approach to do so is with fully homomorphic encryption. With fully homomorphic encryption, you're usually in a client-server setting. You have a client that has some data, possibly sensitive. The client can encrypt the data, send it to a server, and we have a server that then evaluates some function on the data that you tell the server to do. And then the server sends you back the result. You could save on the computation, you decrypt, you get the result, everything's nice. So it took quite a long time to figure out how to do this until in 2009, Craig Gentry came up with bootstrapping. And to give you an idea of bootstrapping, we can think about a ciphertext in homomorphic encryption. We usually think we can think about this as something that contains our message. In this case, you can see this at the left, at the top, right? Which could it be in the higher bits of the ciphertext, and then you have an error in this case in the lower bits of the ciphertext, and then you do an operation, and this error grows, right? So at some point you have to get rid of this error or refresh it. And this is what bootstrapping does. And the idea is once you have a big error, you simply encrypt it again with the same scheme. You also encrypt your secret key. You perform a decryption, but encrypted. And then you get out the message where the error is reduced again. And then you can just repeat this over and over again, perform operations in between, and you can compute on the data, encrypt it as long as you want to. For the purposes of this talk, it's actually enough to know that you can do this. We can treat bootstrapping as a black magic, which if you start dealing with bootstrapping, this is also what it feels like. So this is kind of appropriate. Basically, we have a message encrypted which has a large error. You put it into a black magic box and you get out a message that has a somewhat lower error. Now, all of the FHE schemes that are kind of in use today use this methodology, but we're going to focus on mostly one scheme today, which is the TFHE scheme. And the TFHE scheme is based on two assumptions. First, the learning with errors problem. We are only actually even interested in the parameters, which we have to kind of know to understand the results later. But basically for learning with errors, we have a plaintext modulus, we have a vector size n, we have a ciphertext modulus, and then we have some distributions that influence our security. And the ciphertext in LWE, which is our default ciphertext, is a number modulo q, and then also a vector with coefficients modulo q. And we also we need this for our black magic box. We also need ring learning with errors, where it's super similar. We also have a plaintext modulus. We have a polynomial degree in this case instead of a vector size. We have a ciphertext modulus, and then we also have distributions that we fix usually to small values. And here we do get out two polynomials for ciphertext instead. So it's 2 times n coefficients in a sense, right? We just have to save the coefficients of the polynomial. But we don't really have to, we have to know this to understand how we choose parameters later on a bit, but we don't really need to care how these ciphertexts are constructed. What we can do then is, if we have an encryption, if we have a ciphertext, we have some basic operations, we have a negation. That is pretty straightforward to do. We have an addition that slightly increases the error. And we also have a constant multiplication where you can take a small constant and multiply it with the encryption. And then we just get the encryption of the message multiplied by this constant. And all of these like have more or less a little influence on the error, but yeah, these all work nice. And there's one problem. We cannot do all of the computations we want to do only using these operations. So what we can do in TFHE is we can do actually programmable black magic. So while we'll do bootstrapping, we also compute a function. So you start out with an encryption of M, you put it into our magic box, but a programmable magic box, and you get out an encryption of a function that you wanted to evaluate, right? This can be like any function, it can be nonlinear function, it can be a lookup table, whatever you want it to be. And one cool thing is that we can actually slightly modify bootstrapping, and we get out something called multi-value bootstrapping, where we can somewhat for free produce many more outputs. So we have the same input, but we only need to do an expensive computation once, and then we can produce a lot of outputs for free. This is all fine, but how do we actually use this in practice, right? So we have an unencrypted computation. How do we now go to an encrypted computation using TFHE? And one of the most interesting research directions there has been to use transpilation. And transpilation is basically like compilation. So you take some code, you break it down into fundamental operations, but then instead of putting out binary code, you put out FHE library code. And since you put out more code, it's called transpilation, not compilation, but the thing is basically doing the same thing. And in our case, we started out with something called the FHE transpiler as the baseline, which took C++ code, it threw it into a high-level synthesis tool called XLS, which produced a so-called netlist, which is a circuit that represents this, or the netlist contains a description of the circuit, which you then can use to further transform down to a binary circuit. We use, in this case, the FHE transpiler uses Yosys. And how is the performance of this? Well, you have, in this case, for the FHE transpiler, you have a direct translation by Yosys. There is a small optimization they do, which is, I showed you earlier that we can do negation. So inversion is kind of free if you encrypt bits, right? But there are no other optimizations during synthesis, and also no optimizations post-synthesis. And we wanted to change this. So we changed what Yosys does, and we also added a post-processing step to output the more efficient circuit. And the first step to do so is we have to start at the back, and we have to start about, okay, how do we actually take a Boolean circuit and map it to homomorphic encryption, right? And so what you do is you have multiple gates. Yeah, in this case, you have maybe like two input gates and 3 input gates. And you have to combine the inputs into one ciphertext so you can do the programmable bootstrapping. And the way we do this is that we simply compute a binary composition. So we take 1 bit multiplied by 1, we take another bit multiplied by 2 and add this on top, because we have a multiplication with constants. We have addition, right? We can do all of this for free. And so what we do is we do binary composition, and then we can throw this into our programmable magic box, and we get out the result of the gate that we want to compute. The other thing that we then have to also worry about is obviously fixing the parameters to handle all of this, right? You have to be a bit careful there, but we will see later what the impacts are there. All right. We did some optimizations here. So what did we do after processing? Well, I told you we have this magical thing called multi-value bootstrapping, right? Where we can compute multiple functions somewhat for free. So in this case, what we do is we group gates that have common inputs, right? So you can see at the bottom row here, we have gates which have like the same inputs. And instead of saying these are 3 gates which require 3 bootstrappings for us to do, we can group all of them into 1 gate which produces 3 outputs, right? So instead of having, so you have this simple notation G3, which says, oh, this is a gate with 3 inputs. And then you have this notation G33, which says, oh, we have a gate with 3 inputs and 3 outputs in this case. You have to be a bit careful. Yeah, one might want to take the gate at the top and just put this in the same group. But then we have cyclic computations, and this is not really something we know how to deal with. So you actually can only do these groupings at the same depth in the circuit, right? Because you could also just check all the parents, but this gets very expensive very quickly. So yeah, we decided to only do it at the same depth in the circuit. The other thing that we realized is, and this is something you have to tackle during synthesis, is that we can represent adders more efficiently when we are in a lookup table-based environment. And so usually what the synthesis tool will output is an addition using 2 gates. This is a 2-bit addition, right? You have like a 2-bit gate with 2 outputs, and then you have a 3-bit gate, and this will give you your sum. So this is something the synthesis tool will output for a 2-bit addition. What we can also do is simply add all the inputs that we want to add, throw them into a gate, and decompose the outputs. Because we have native addition, we can simply substitute addition during the synthesis process with native addition and only decompose to the output. So what parameters do we need for this? Well, it depends is the correct answer. It mostly depends on what you want to be, how many bits you want to be able to put into one ciphertext. So if you want to be able, to only put 2 bits into a ciphertext, so you have, then you have the binary case. Then the most important thing to look at is the polynomial degree, which is also why it's in the name. Then you can get away with a polynomial degree of 2 to the 11, getting 128-bit security. The other parameters are mostly there for reference if you're interested, if you know what they mean. If you want to do multi-value bootstrapping, you can stay with 2 to the 11. You slightly have to increase some parameters. You need additional space there to do this, but this still works. Or like it works up to a plaintext modulus of 8, actually. And then when you want to do even bigger lookup tables, so let's say a 4-bit lookup table where you want to compose all the inputs, then you already need to increase your polynomial degree to 2 to the 12th. And if you look to the rightmost column, this totally sucks because our bootstrapping time increases by a lot, right? So if we go for the smallest parameter set, we can do a bootstrapping in our benchmarking environment. It took around 2.24 seconds. But for increasing the polynomial degree, increase this time to 0.58 seconds. So yeah, massive increase. And so even though you might be able to reduce the number of bootstrapping using larger gates, it might not necessarily gain you performance. And if we simply look at bootstrappings, this is only like an excerpt from the paper. There are many more examples there. We can basically, using our techniques, we can almost always reduce the number of gates. There's one, I want to highlight 2 examples here. The one is at the bottom, where we have a string reversal. There are no additions in a string reversal, so using adder substitution surprisingly doesn't make a difference. Who would have thought? And then there's also a square root computation, and something funny happened there using adder substitution. It actually got much worse. What is going on there? Well, the issue is that when you have constant additions and then you give this to a synthesis tool, it is very efficient at merging these into the lookup table logic. And we detected those cases and said, like, don't substitute constant addition because it's better to just like merge it with the surrounding logic. But in this case, the constants were like 1 or 2 gates away. And so we couldn't detect them in CHES directly. This happened afterwards when optimizations were taking place during the translation to lookup tables, where we couldn't interfere there anymore. And so in this case, adder substitution turned out to be worse because of the constant bits that could be fused with surrounding logic. But in all other cases, we got better results here. And then if we look at how this translates to timings, I also included the 4-bit logic here. You can see that for like 3 bits, we got the best speed ups. So we have using all optimizations, we got speed ups around 2 to 3, and then also excluding adder substitution, we got even more speed ups sometimes. I think the columns are switched here, if I remember correctly, the numbers from the paper. So they probably have to be the other way around. But yeah, so using adder substitution definitely helped in most cases. But in some cases it was detrimental, most notably in the square root case. But you can see that for 4-bit lookup tables, because we have to increase the parameters so much, like we have less bootstrappings, but it's not worth it, right? If you have to increase your parameters to do these optimizations, you will be slower. So don't do that. What else is in the paper? We have more use cases in there that you can take a look at. We also have further analysis of the results with the edge cases. There's a novel approach for selecting the coefficients of rotation polynomials for multi-value bootstrapping. So if you are interested in that, have a look. And I think also, well, it's not in the paper, but it's open source. It's a super easy to use implementation of multi-value bootstrapping. I'm not aware of anything that is that easy to use. Basically, and this is all credit to Kamil, by the way, who put a lot of effort into this. Basically, you can just generate these lookup table constructs passing in C++ lambda functions, where you have an input X and your plaintext modulus P. You can do whatever you want in there, and it will generate you a lookup table for this. And then you call a function eval lut amortized, and you get out the vector of outputs. And this is super nice to use. It made it super easy to generate all of this code. And I think I'm not aware of any implementation of multi-value bootstrapping that, like, there are 1 or 2 others, but they are not easy to use. So if you need this, have a look at the GitHub repo. There's also 2 related works that since have taken off a bit that I would like to mention. There's HEIR, which is something Google puts a lot of effort in. It's a compiler for homomorphic encryption, which uses the multi-level intermediate representation. And basically you have many levels of intermediate representation where you can perform optimizations, and they also have a Boolean intermediate representation for optimizations that you want to do on a Boolean level. Why is this nice? Because you can do optimizations like I presented here today, like we did in our work, together with other optimizations. And so yeah, definitely if you're interested in this line of work in homomorphic encryption, I would recommend checking that one out. I'm not affiliated with them, by the way, I just like it. And there's also a recent ePrint from Sergei Karpov. I showed you before that we could like add to inputs and then just decompose, right? Our adder substitution. In his recent work, it's an interesting work. He even took this idea further, and he generalized encoding functions and totally separated this from the evaluation logic. And then he also provides a heuristic on grouping these gates. So this is also something interesting to have a look. I would recommend you to read his paper. And with that, I'm happy to take any questions. Thank you.
So any question from the audience? All right. Okay. So maybe I have a question.
Sure.
So when you know, it's kind of like you are formulating the whole scheme again. Have you compared with the scheme with the other homomorphic schemes?
So the scheme doesn't change, the parameters do. And basically the top row is a secure instantiation of the scheme that is from previous work. We didn't come up with this parameter set. The two new ones are for the multi-value bootstrapping only.
Okay.
Yeah, and we checked security using the lattice estimator that it's 128-bit secure, and the correctness is also checked.
How about the actual performance, like the speed and also the bootstrapping efficiency?
So since Kamil wrote the library, if you're interested in a lot of the details, send him a mail. What we did focus on, we had to switch benchmarking platforms in between due to reasons, and the library uses the Hexel arithmetic layer. If you're familiar with this, it's a library by Intel which does AVX accelerated NTT, right? And it also uses FFTW for the FFT. So yeah, it uses common libraries, so you get the performance from these basically, and then there's a slight overhead obviously from the surrounding logic, but this is the main computational bottleneck. We use common libraries for that.
Okay, good. Any questions? If no question, let's thank our speaker again. Thank you. All right. Okay, so let's have the second talk. It's about fast and accurate, efficient full domain functional bootstrap and the digit decomposition for homomorphic computation. The speaker is Shihe Ma. Let's welcome our speaker.
Good morning, everyone. I'm Shihe Ma from Tsinghua University, and today I will present our work on full domain functional bootstrap and digit decomposition. So my presentation will begin with an introduction to the functional bootstrap of TF-HEW, of TF-HE and FHEW, and I will describe two important algorithms related to the functional bootstrap. The first one is called the full domain functional bootstrap, and the second one is the homomorphic digit decomposition. I will describe the existing works and our contribution. So the fully homomorphic encryption is just anyone with the evaluation keys can compute unencrypted data without access to the decryption key. And it is often used in outsourced computation. And the original concept was by Rivest, Edelman, and Dertudis in 1978. And the first FHE construction is driven by Gentry in 2009. Today, most FHE constructions are based on noise encryption. And to handle the noise growth during computation, we need an operation called bootstrapping to refresh the noise level by computing the decryption function homomorphically. And we mainly use two generations of FHE now. The first one is the second generation FHEs, for example, BGV, BFE, CHES. They're based on RLWE and has a single instruction multiple data property, but has a relatively slow bootstrapping. And we also have the third generation FHEs like CSW, FHEW, and TF-HE. They are LW based, has very fast bootstrapping, but is single instruction, single data. And we will mainly focus on the third generation ones in this work. And we often set the plaintext modulus to 4 to compute Boolean arithmetic, and we need to deal with two schemes here. The first one is called the base scheme, which is something the user uses to encrypt its scalar message, and we often use LW as the base scheme. We also have an accumulator scheme, which is used only in bootstrapping and invisible to the user. It encrypts a polynomial, and we often use GSW-like RLW or GSW-like untrue for this accumulator scheme. And the core of the bootstrapping is an operation called blind rotation. And as a toy example, we look at the cyclotomic ring with a dimension of 4, and we can multiply a polynomial of degree 3 by x to the exponent of -1. So all the coefficients, they are rotated to their left by 1 position, and A0 is wrapped around and negated. So if we can rotate these coefficients by an offset that is equal to the plain text encrypted in the input LW ciphertext, and we just look at the constant term of the rotated coefficients, then roughly speaking, we are selecting one of these coefficients using the input plain text. And so this blind rotation is similar to a table lookup, where the table entries are just the polynomial coefficients, and the index used for lookup is the plain text encrypted in the LW ciphertext. And usually the inner rotation, they are realized either with external products or ring automorphisms. And by a careful design of the text vector TV, which is just the polynomial we want to rotate, we can compute an n and 2 gates in each functional bootstrap. And this allows us to compute an arbitrary circuit. So this is the notion of the gate bootstrap, where we compute Boolean gates on binary messages during each bootstrap. And if we move on to small precision integers and replace the gates with lookup tables, we have the functional bootstrap, which is what we will focus on today. And in a typical functional bootstrap, this is its workflow. So we have a LW ciphertext whose modulus is twice the ring dimension of the RLW scheme. We use blind rotation to rotate the text vector ending with an RLW ciphertext. Then we extract the constant term of the rotated text vector into an LW ciphertext. Then with some model switching and key switching, we will end with another LW ciphertext with the original secret key, the original dimension, and the original ciphertext modulus, and which can be used in the next bootstrap. And in these intermediate LW ciphertexts, which are outlined in green, we can perform homomorphic additions or multiplication with constants. And I'd like to remark on the size of P. So ideally, we want to set the plaintext modulus P as large as possible, because the larger P is, the higher precision the table lookup will be. However, the maximum P is bounded by this value, n divided by BMS, where BMS is the bound on the modulus switching noise, and which is further determined by the ring dimension and the secret distribution. So this bound for the maximum P comes from the input LW ciphertext. It has a fixed modulus of 2n, and the noise will take 2 BMS of it. So only n divided by BMS is left for P. And for this work, the maximum P is 5 bits. And the functional bootstrap, although very powerful, has 2 limitations. The first one is called the negligibility, which means if you imagine the lookup table as a one-dimensional array, then the later half is just a negated copy of the first half. So we cannot evaluate an arbitrary lookup table during the functional bootstrap. And common workaround is to add 0 padding bits so that only half of this lookup table is used. However, this will cause a loss of precision, and also some after some homomorphic additions or constant multiplications, these 0 padding bits may be consumed, and which makes the following bootstraps impossible. And the solution to it is called the full domain functional bootstrap, proposed by Kuzniak and Shield and Chilotti et al., the two teams in 2021. And the second limitation of functional bootstrap is the low input precision. So usually we have P that is as large as 4 to 5 bits. And if we want to increase the size of P, the running time of this functional bootstrap will increase exponentially in the bit length. And a possible solution to this is called homomorphic digit decomposition, which means we just break high precision LW message into multiple small precision ones, and we can compute functional bootstraps on these small precision ciphertexts. And our contributions is that we have designed faster FDFB algorithms and faster homomorphic digit decomposition algorithms, and we have also implemented existing and our algorithms in OpenFHE. So roughly, we have categorized existing FDFB algorithms into 3 types. The first one we call it select MSB. So suppose we know the most significant bit of the input LW plaintext, then we can compute our arbitrary LUT within one functional bootstrap, since only half of the lookup table is used. However, we cannot know the MSB in our real cases. So each possibility of this MSB corresponds to a different test vector. And the idea of this type of FDFB is that we use an encryption of MSB to choose the right test vector and then rotate it just in a usual functional bootstrap. And the first algorithm is called WPPBS from CLOD21. They use 3 functional bootstraps and they use BFA multiplication to combine these values. And since these 3 bootstraps share the same input, they can be replaced by a single multi-value bootstrap developed by Karpov et al. In 2019. And the second algorithm is from Kuzniak and Shield in 2021. They will compute many encryptions of b to the power of I times MSB for various I, and use it to select the right test vector while achieving slow noise growth. And finally, they just rotate the selected test vector. And the second category we call it the half range, and the representative of it is the evolve-found algorithms from LMP22. And so the idea is that they first double the ciphertext modulus, which will introduce an unknown MSB to the underlying plaintext. Then using a functional bootstrap, they remove this MSB, which will create a 0 padding bit. And so with this 0 padding bit, we can compute any LUT in a second bootstrap. And the final category is called composition, and they just express the LUT as the sum of a pseudo-odd and a pseudo-even function, and each one computable with 2 bootstraps. So we first improve upon the evolve-found algorithms. In the first bootstrap, we use a compression function that will compress the plaintext from the full plaintext space into half the plaintext space. And this will create 0 padding bits in the result. And then just like in evolve-found algorithms, we can compute arbitrary LUT with a second functional bootstrap. And so the compression function is not necessarily the identity function. It can be a permutation of the message space, for example, the one illustrated here. And this algorithm achieves 1 bit loss of P, which is half a bit better than the previous one. And such a loss of P is actually optimal for this type of FDFB. And we have also improved upon the WPPBS, and mainly with refined noise analysis. So in a regular BFA multiplication, all the polynomial coefficients are non-zero. And however, in this very special BFA multiplication used in WP-PBS, only the constant term is non-zero. So in our noise analysis, we can replace this polynomial multiplication with a stereo one, reducing the noise variance growth by a factor of n. And with smaller noise, we can use more compact parameters, which can lead to faster running times. And finally, as an alternative, we can replace BFA multiplication with LW to RLW patching and extra bootstrap. So although we need one more bootstrap here, the noise growth is significantly reduced compared to the BFA multiplication-based ones. So again, we can use even more compact parameters. So example for the patched message is given here. So if the input message is negative, we will rotate this polynomial to its right, ending with m negative in the constant position. Otherwise, we will have m positive in the constant position. And here is an experimental comparison of previous and ours FDFB. And we have reduced running time by up to 40% of a single bootstrap. And in terms of homomorphic digit decomposition, it will decompose an LW ciphertext with a large p into multiple smaller LW ciphertexts with small p. And we assume here that all the ciphertext moduli are powers of 2. The core idea is that we approximately clear the lower bits of the input plaintext so that we have enough room to hold the model switching noise in the second step. So by modulus switching this result to a lower modulus, the second lowest digit will now become the lowest digit, which allow us to extract it just by modding down. And by repeatedly performing this procedure, we can fully decompose these LW ciphertexts into many smaller LW ciphertexts. And this decomposition can be used in the tree-based or chain-based LUT evaluation proposed by Demarins et al. In 2021. And for special functions that depend on the MSB of the input message, this computation can be especially efficient. And we have given two improved versions of the digit decomposition. And the first one is called the home decomp reduce. So the observation here is that we want to make some room to hold the model switching noise. So there is, it's not actually necessary to clear the lower bits. Instead, we can just reduce the size of lower bits. And this will allow us to use only one bootstrap to extract a digit. And this method supports 4-bit digits at most. And the second one is called home decomp FDFB. And like in previous works, we also clear the lowest bits, but with our new FDFB compressed algorithms. So we can extract the digit with 2 bootstraps, and we can support extraction of 5-bit digits. So compared to their previous counterparts, our algorithms can reduce the number of bootstrap to extract a single digit by 1. And this is a very significant efficiency improvement. So this is the experimental results. And the x-axis is the number of the bits in the input ciphertext modulus, and the y-axis is the milliseconds required to fully decompose the input message. So you can see our red lines costs much lower time than the blue ones. And since this work was done in 2023, there has been various papers released during this time, and some optimizations used in them can also apply to our work. For example, we can replace the accumulator scheme by RGSW-like untrue, and this will greatly reduce the number of external products and will lead to a smaller public key size. We can also use the ring automorphisms instead of external products for smaller public key size, and also either in external products or ring automorphisms, we can use approximate decomposition instead of exact decomposition for more compact parameters. Finally, with the trace-based LW to LW patching from Eurocrypt 24, we can greatly accelerate the patching step and obtain much smaller patching keys. And okay, sorry, I updated the slides too late. So there's another type of FDFB I would like to mention. It's kind of FDFB that uses odd plain-text modulus. So the first one is listed here, the paper from Inscript 23. They use conversion between BGV-like and BFV-like LDB ciphertexts, which means they can move the capacity bit in the input LW ciphertext to the position of the MSB, thus creating a zero padding bit, and this allows them to realize FDFB. And the second paper is just presented by Nicholas Bong yesterday at CHES 2024, and they also need to use odd plain text modulus, but they don't require this conversion step. And both FDFB algorithms achieve the same function. They are very efficient. They need only one bootstrap, and they have one bit loss of plain text space. And compared to our FDFB compress, they require one less bootstrap. But they need an extra capacity bit in the input and requires odd plain text modulus. And finally, I would like to remark on the remaining capacity problem. So in this work, the parameters are chosen so that only correct decryption of the results are guaranteed. However, for some, especially for those BFV multiplication-based methods, the remaining capacity may be so small that it will not allow for any subsequent, say, constant multiplication. So if we want to incorporate these algorithms in real applications, we may need to choose the parameters with more care to control the noise growth. And thank you for listening.
Any question? I have one question. It's about, it seems like this scheme is kind of a hybrid kind of combination with different kind of operations. Is that right? Like I see that one of the type of the algorithm is, for example, is combined with the BFV multiplication.
Yes.
So from this point of view, have you ever considered about the further kind of development into another kind of popularize this kind of algorithm just to kind of take advantage of different advantages of different kind of schemes to combine them together as a better scheme? Is this what you want to present?
Well, it may be a possible way, but I think combining multiple schemes together is itself a challenging task.
Okay.
And sometimes you just don't improve the efficiency. The efficiency may be even degraded.
Okay.
So that's what may work on later.
Okay. The second question is, have you ever considered about to accelerate this one using the hardware design techniques?
Using what? Hardware?
Yeah, hardware, because the one you are implementing is on the software, right?
Yes, but no, sorry, we are not experts in hardware design.
Okay, okay. All right, okay. No question? Okay, so let's thank our speaker again. So I think the third Third one is online, and the title is Faster Bootstrapping via Modulus Raising and a Composite Entity. The speaker is Ying Liu.
And today I will present our research on faster bootstrapping via modulus raising and composite entity. This work is a collaboration with our team members, and we are grateful for the support from the key laboratory of cybersecurity defense at the Institute of Information Engineering, Chinese Academy of Science. Okay, let me introduce our latest research results on bootstrapping acceleration in homomorphic encryption at today's conference. In today's presentation, I will cover the following sections. First, I will provide a brief introduction to homomorphic encryption, followed by our main contributions and technical details. Then, I will share our experimental results, and finally conclude with a summary of our work. Let's begin with a quick overview of the homomorphic encryption. There is a straightforward and vivid signal that can describe homomorphic encryption. There is a user who possesses a series of private data M1 to Mn. He wants to perform some functions such as f on this data, but his computational ability is not enough to deal with them. So he wants a server helps him deal with the data, but he doesn't want to give away the concrete data of the M1 and M1 to Mn. So he encrypts the M1 to Mn and gets n ciphertexts. He sends the n ciphertexts to the server. The server, after receiving the data, can perform operations on the encrypted data corresponding to what would be done on the plain texts, all without decrypting them. The server then sends the results back to the user, who can decrypt them to obtain the desired computation results. Homomorphic encryption allows computations to be performed on encrypted data, with the results remaining encrypted and equivalent to those obtained by performing the same operations on the plain texts. This feature makes homomorphic encryption highly valuable in scenarios where data privacy is crucial, such as in cloud computing and secure data processing. Homomorphic encryption schemes can be classified based on the type and depth of computation they support. These categories include the partially homomorphic encryption, somewhat homomorphic encryption, labeled homomorphic encryption, and fully homomorphic encryption. The first one, partially homomorphic encryption, supports only a single type of operation, such as addition or multiplication, but not both. For example, the L-gamma encryption scheme supports only multiplication. The second one is somewhat homomorphic encryption, which allows a limited number of operations, but there are still restrictions. The BGN encryption scheme is a typical example, supporting a limited number of additions and multiplications. The third one is labeled homomorphic encryption schemes, which support more complex operations but has restrictions on the depth and computations. Examples include the BGV and BFV schemes, which are suitable for exact arithmetic operations. These schemes allow computations across multiple layers of encryption, but require bootstrapping to refresh the ciphertext when the noise reaches a certain threshold. The first one is fully homomorphic encryption, which is the most advanced form of homomorphic encryption, supporting arbitrary depth computations. Schemes like CKKI's FHEW and TFHE fall into this category, allowing unlimited operations on encrypted data. From an application perspective, these encryption schemes serve different purposes. For instance, BGV and BFV are well suited for exact arithmetic operations, CKKS for approximate arithmetic operations, and FHEW, TFHE for Boolean operations. As we can observe from the slide, when a message is first encrypted, the noise level is relatively low. However, as homomorphic operations are performed, the noise gradually accumulates. Once the noise surpasses a certain threshold, the ciphertext can no longer be correctly decrypted. Therefore, it is essential to employ a technique that can reduce the noise within the ciphertexts, allowing homomorphic operations to continue indefinitely. This technique is known as bootstrapping. Currently, bootstrapping is the only method available for achieving fully homomorphic encryption. It effectively refreshes the noise in the ciphertext, enabling further homomorphic computations. The essence of bootstrapping is to homomorphically compute the decryption function. However, bootstrapping is computationally expensive, and improving its efficiency is a critical research challenge. In this slide, we explore the bootstrapping process in the FHEW and the TFHE frameworks. Bootstrapping is a critical technique in FHE that allows encrypted data to be refreshed. We start with the encryption of message I'm using the LWA scheme, which produces a ciphertext BA as the input of the bootstrapping. The goal of bootstrapping is to transform the ciphertext into a new ciphertext that provides the lower noise of the function of Fm. The process begins by constructing an accumulator ACC using the ring LW encryption of the term x to the power of b multiplied with test polynomial. For each iteration I from 1 to n, the accumulator is updated via the controlled multiplier operation CMUS, which computes external products between ring LWE ciphertexts and the bootstrapping key stores as ring GSW ciphertexts. The core part of bootstrapping is blind rotation performed by the CMUS case, which involve n external products between ring LWE ciphertexts and ring GSW ciphertexts. During the homomorphic computation of the decryption function, implying the homomorphic mod Q operation is computationally expensive. Blind rotation maps the decryption function b minus a times s to a power of x, leveraging the negative cyclotomic properties of the ring to achieve the mod Q operation at no additional cost. To control noise, each external product calculation first requires the decomposition of the ring LWE ciphertext using the gadget decomposition G inverse, and we can decompose the ring LWE ciphertext AB in RQ to 2D terms in RQ. The bootstrapping key is then generated based on this decomposition method, which essentially means that encrypt the LWE secret key using ring GSW. And the decomposition method decides the gadget matrix in ring GSW. So in each external product, we need to compute the matrix vector multiplication involving 2D times 2 polynomial multiplications. So the whole blind rotation needs 2D times 2 times n polynomial multiplications. The computation cost is quite huge. Therefore, the efficiency of polynomial multiplication significantly impacts the overall bootstrapping efficiency in FHEW and FHE schemes. Next, I will introduce our contributions and technical details. Our main contributions include the design of a new external product coupled with modulus raising technique and composite entity technique, which significantly accelerates the bootstrapping process in the FHEW scheme. We also propose a new blind rotation using the new external product and apply it to AP automorphism blind rotation and untrue. Finally, we gain a 1.7 times speed up over the original FHEW scheme. Now, let me introduce our composite entity technique. Throughout the field, it has long been assumed that using entity primes is not feasible when dealing with composite moduli. This belief stems from the fact that the entity algorithm requires the modulus Q to be a prime number, satisfying Q equals to 1 mod 2n, where 2n is the degree of modular polynomial of the ring RQ. This condition ensures the existence of a 2nth primitive root of unity, zeta q, which possesses periodicity and symmetry properties. These properties allow us to use the parts of zeta q to decompose the modulus polynomial, such as the x to n at 1, thereby mapping polynomial multiplication into several rings of lower order. However, in the domain of side-channel security, HP22 introduced a method for constructing a primitive root of unity for composite modulus Q, which is the product of two entity primes Q1 and Q2 using the inverse Chinese remainder theory, ICRT. For two entity primes Q1 and Q2, there exists corresponding to nth primitive roots of unity mod Q1 and Q2. We call them zeta Q1 and zeta Q2. By applying ICRT to zeta Q1 and zeta Q2, one can obtain a root of unity mod Q that maintains periodicity and symmetry, which can then be used for entity computation. Leveraging this property, we recursively apply ICRT within a binary tree structure to construct roots of unity for composite numbers that are products of multiple entity primes Q1 to Qk, as shown in this slide. Consequently, when working with such a composite modulus Q, we can directly compute the entity in the ring RQ without utilizing RNS to decompose the polynomial ring to several small rings. Based on the composite entity technique, we have designed a new method for computing the external product. Unlike traditional external product approaches that involve gadget decomposition of the ring LW symplectices, our method focuses on processing the ring GSW encryption. Specifically, we lifted the modulus of the ring GSW symplectices from Q to Q, while keeping the ring LW symplectices unchanged in the ring RQ. So the external will be computed in the ring RPQ. And we need to convert the modulus from PQ to Q after multiplication in RPQ. This approach does not increase the number of ring LW ciphertexts, and correspondingly, the ring GSW ciphertext still contains only 2 by 2 polynomials. As a result, the number of polynomial multiplications required for each external product is reduced from 2D times 2 to 2 times 2. This significantly reduces the theoretical complexity and the implementation cost of the computation. By leveraging modulus reasoning and composite entity techniques, we can construct a hybrid external product computation method. This approach simultaneously utilizes gadget decomposition and modulus reasoning, followed by polynomial multiplications within ring RPQ using composite entity. Before the next external product operation, the modulus is also need to be mapped back to Q by dividing by P. This method allows for better noise management compared to solely using the gadget decomposition technique. As can be seen from the two figures, the original method consistently requires more entity operations and Hadamard multiplications compared to our method. Additionally, as the decomposition loss increases, the gap in the number of required entity operations and Hadamard multiplications between the GINS method and our method widens further. Although the noise growth is similar between our method and the GINS method, it is evident that our approach offers better computational efficiency. Now let's take a look at our experimental parameter settings and results. All our experiments were conducted on an Intel Core i5-12500 CPU with 64 GB of RAM running Ubuntu 22.04. We provide two sets of parameters which support 96-bit security level and 128-bit security level separately. We executed 5,000 time tests to average the results of the running time of bootstrapping. The results show that our scheme reduces the computation time significantly, achieving a 1.8 times speed up in binary blind rotation compared to the original FHEW scheme. Additionally, we compared different blind rotation key sizes to evaluate the performance of our approach. Using our blind rotation method, the blind rotation key size is reduced by 50%, which also decreases storage requirements dramatically. In conclusion, we designed a new external product using composite entity and modulus reasoning technique. We apply this new external product method to contrast a more effective blind rotation. Then our research effectively accelerates the bootstrapping process in the FHEW scheme. Compared with the original FHEW scheme, we can gain a 1.7 times speed up, and we reduce the key size of blind rotation keys about 50%. These advantages bring FHE closer to practical implementation. Moving forward, we plan to further optimize these techniques and explore their application in other homomorphic encryption schemes. Finally, I'd like to thank you everyone for your attention. If you have any questions or topics of interest you'd like to discuss, please contact us. Thank you.
I think the speaker is not online, and maybe we just finish here the session. Thank you, everybody. Enjoy.